You have probably heard the story of the famous scientist Sir Isaac Newton sitting by an apple tree and watching an apple fall from the tree to the ground, and this was his inspiration for what he would later describe as gravity. Whether the story is true or not is for historians to decide, but today we're going to measure gravity. If you pick up your favorite introductory physics textbook and turn to the page that has reference information on it, you are likely to find a reference for the acceleration due to gravity, denoted little g, with a value of 9.80665 meters per second squared. This is the value we are going to approximate with today's little experiment. Experiment 1 involves dropping a pencil from a predetermined height, 2 feet in this case, while measuring the time it takes to drop. We will repeat the experiment 25 times to get a good sample of data. Here is the data from experiment 1 presented in a histogram. For example, this bucket represents all the times that fall between 0.25 and 0.26 seconds. As we see, the mean value or average value is 0.3 seconds right here. And the range of observations is between 0.2 and 0.45 seconds. Let's see what effect this has on our calculations for little g. If we use our equation h minus g over 2 times t squared equals 0 and rearrange, we can solve for g. And doing so produces a g value corresponding to each time observed. The average value of doing this is this mean value, which is 49.9 feet per second squared. If we instead use the least squares estimate, we can estimate a single value of g that best describes our equation given the data we've observed. The least squares estimate is 35.5 feet per second squared. The actual value that corresponds to the 9.81 seen in the textbook earlier in this video, when converted to English units, is 32.2 feet per second squared. So our initial experiment gets us relatively close. Let's see what happens in experiment 2. In experiment 2, we'll increase the height to 5 feet and then repeat the preceding experiment. Experiment 2, we collect more data, 57 total trials. The distribution now looks more symmetric. The mean value is seen to be 0.64 seconds. Just like the first experiment, we process our data resulting in an average value of 25.6 feet per second squared and a least squares estimate of 23.3 feet per second squared. These values don't seem better than those found in experiment 1. This is primarily due to the poor experiment design. While on the ladder trying to run the stopwatch and while leaning over to place the pencil in the correct height, I introduced a lot of variation into the experiment that wasn't present in the first experiment. Any gain in accuracy due to the higher height was negated by my drop in precision of drop height and timing. In our third and final experiment, we'll use the slow motion feature on the iPhone to capture and drop 2 feet again. Slow motion footage is captured at 240 frames per second. Therefore, if we count the number of frames it takes for the pencil to drop and divide by 240, we will get the actual time in seconds. The most difficult part of this process is telling when the pencil actually starts to drop from the top of the ruler, as can be seen here in showing the frame-by-frame replay. Because the camera sits lower than the start of the drop point, and we are using the frame-by-frame change in pencil shadow against the wall to estimate the first frame, there is very likely a tiny delay that is unaccounted for in our frame count. Therefore, we will add 1 frame to each trial to mitigate this error. Experiment 3 has 28 total trials, and the data is shown in the histogram. Notice how narrow the spread of times are compared with our previous experiments. The average value is 0.35 seconds. Our final results are in. The average and least squares estimate are nearly identical at 32.5 feet per second squared, while the actual value is 32.2 feet per second squared. The variation shows a tight range of values, much better than our previous 2 experiments. Here is a comparison of the data from each experiment. We see clear evidence that the variation, or the spread of the sample drop times, reduced with each experiment. And here are our final least squares estimates of G for each experiment. Number 1 coming in at 35.5 feet per second squared, 2 at 23.35 feet per second squared, and finally 3 at 32.5 feet per second squared. Our experiment 3 result is much more precise and accurate because our experiment design removed many errors the first 2 experiments suffered from. This demonstration shows the importance of experiment design and the corresponding goal of removing all possible sources of variation due to the experiment setup.